So, welcome to my dear friends and learners. Uh, I'm going to start one so very brief course on Steam Turbine. So, this is a very fundamental theory and application. Um, so, I have thought that I will complete this lecture series in uh, by elaborating few topics like steam turbine principle and its operation, then the construction, then the regenerative and reheat cycle, its control strategy, and the steam cycle. So basically, the this today's lecture will be on principle and its operation. What is steam turbine? In steam turbine, basically the working fluid enters at high pressure and it acquires increased kinetic energy as it's expand to a lower pressure uh, in a ring of fixed nozzles. You know, nozzle is such a very simple but widely used uh, uh, mechanical device which is used to uh, regulate the flow and its direction. The stream of fluid then undergoes a change of momentum as it flows through a passage between blades which are attached to the rotor. Okay, and then the component in a direction tangential to the uh, circle of rotation, it produces the output torque to the shaft and it rotates. Okay. Uh, in turbines, the fluid undergoes a continuous steady flow process and the speed of flow is very high. Okay. For this reason, in compared to other prime movers, uh, in a small machine, it can handle large mass flow and large enthalpy transfer, and this all these things it's entire the energy transfer will be a adiabatic process because here heat transfer will not take place. So this is the cross section. This is the 2D axisymmetric view of a turbine. So you see, this is the nozzle. Through this the high pressure steam enters, and those are the moving blades, and while it is flowing through the passage, there is a change of momentum, and the component of that momentum change along this direction will produce some impulsive force as well as the reaction force on the turbine blade, and it due to that force the blade will move and the turbine shaft will rotate. Okay, this we will understand here. Few vectors are working together to produce the torque, so that those we will understand in the subsequent slides. And then there will be again fixed blades which are also called a nozzle, and this is like that several. So one moving blade, one fixed blade. This one set is called one stage, then another stage like that, based upon the power, the number of stages will be decided. Okay. If you want to categorize the turbines, so those are basically of two types. One is impulse turbine, another is reaction turbine. So as the name suggests, this in case of impulse turbine, the torque produced in the rotor shaft, that is due to impulsive force, and in the reaction turbine, the rotation of the turbine is taking place due to reactive force. So you can one simple example, you can understand what is impulsive force and what is reactive force. Impulsive force means, suppose one pin or nail you want to insert in a uh, uh, wood, inside a wood. So what you will do, in a hammer you are heating. So a very short time interval there is a change of momentum. Those is that force basically, it is causing the, it is due to that the pin is getting inserted inside the wood. So basically that is pt, this high pt is equal to mv, or p is equal to mv by t. Here this t is very within very short period t tends to 0. So this high pressure is developed. So p is equal to mv by t. So as t tends to 0, so this term, this p is abruptly high, and due to that reason the force is getting generated. In contrast, say you are shooting a gun, so there is a backward force you will experience in your shoulder. Those are the reactive force. Okay. So impulse turbine use high velocity fluid jet to strike the blade, as I told. So suddenly once it is striking the blade, is very short interval, it is that there is a high pressure, it is developing in the uh, blade, and that thrust it will cause to rotate the turbine. In contrast, reaction turbine uses pressure and the kinetic energy both, uh, and this while the high velocity uh, fluid is passing through the blade, this will due to the construction of the blade, this there will be a change of momentum which is causing the reaction, and that force is responsible to rotate the turbines. So purely impulse turbines are, you can tell it's a Pelton wheel, and the reaction turbines are Francis or Kaplan. So impulse turbines are best for high head but low flow, whereas the reaction turbines are suited for low head but high flow. Okay. In case of steam turbine, it is neither it is neither it is neither impulse nor reaction types. Perhaps this is the mixture of both these types. Okay. So that's why the steam turbine which are used in thermal or nuclear power plant, Those are called impulse reaction type turbines. Okay. So as I was telling, this is the nozzle or the fixed blade, and this is the moving blade. These nozzles are used to redirect and to slight increase of kinetic energy of the steam jet, and then it is passing through this blade, causing the construction of the blade is such that there is a change of momentum, and the component along this, it is causing the torque and the rotation of the turbine shaft. So steam turbines are also classified into two categories, which are axial flow turbines and the radial flow. But most of the steam turbines are axial flow turbines. So we will discuss these things in more details. So from the earlier discussion, in an impulse reaction turbine, uh, a part of pressure drop occurs in the nozzles, means while it is passing through the uh, fixed blade. Okay, the remainder, the remaining pressure drop is occurring during the passage of the steam through the blades, moving blades. Okay, the blade passage are nozzle shaped, so that the acceleration of the steam occurs partly in the nozzles and partly in the blades. You can see there is a symmetry here. There is a symmetry of this cavity or the passage through which the steam will pass through. Okay, the force of reaction is added to the force resulting from the redirection of the steam to make the total propulsive force on the blade. We will, this statement we will understand using the vector diagram. In most modern reaction turbines, the propulsive force is derived 50% from reaction and 50% from impulsive effect. Okay, so we already understand what is impulse turbine and what is reaction turbine. So the torque produced in the shaft, it's partially due to impulsive force and partially it is due to reactive force. So here this is a you can see this is the nozzle. The first row is the nozzle, through this the steam is entering. Then next it is the moving blade. Then again this is a fixed blade or nozzle, like, and so on. Now if you rotate, you can see, so the steam jets are passing through this. Okay, from that, if we now try to draw, so uh, here you see, so this is the axis of rotation, uh, and this is the plane of rotation. Now here the blade, say this blade is rotating with a velocity u. Now I am representing in vector, so this is your u. Okay, and after the nozzle, while the steam jets are hitting or entering into the uh, surface of the blade, then that is through this. sorry, it is like this. So let's say that is v1, and the angle is beta 1. Then that these two vectors, that means here let me draw. So this is your blade is moving with this velocity. This is that vector, and from here this is the steam jet velocity while it is entering to the moving blade. Now as per the triangle law, so the vector addition triangle law, uh, if the two vectors are in the same direction, two vectors are representing the two sides of a triangle, then the another side in opposite direction will represent the resultant of these two. So now if it is like this, then this we have to complete this triangle. So this triangle is completed, and the opposite direction is this, is representing the resultant of these two vectors. So same here in this triangle, this C1 is the resultant. Okay, while entering, and during exit, say the steam jet velocity is this one, and it is coming in this angle. This is the V2, and this angle is beta 2, and U is in this direction. So in the opposite direction, this is the resultant. Okay. So what we can see, and that is, say this is C2. This is C2. So while the steam jet entering inside the um, moving blade passage, so there are two vector acting. One is the movement of the blade as well as the velocity of the steam. These two resultant, if you are taking, C1 is the resultant vector at the inlet, and C2 is the resultant vector at the outlet. So this triangle is called basically the inlet vector triangle, and this triangle is called the outlet vector triangle. Now just what I am trying to do, this I am just clockwise 90-degree rotated this picture. This picture 90-degree clockwise rotation. And now what I am basically trying, this inlet and outlet triangle I am trying to combine together. So just I am, this red line, say it is a mirror. I am taking a mirror image of this outlet triangle. So this is your V2, and this is your U, and this is your C2. Correct? Now I will again, so you know, now we are trying to find out the component of the resultant vectors at the inlet and at the outlet, which is parallel to the direction of the motion of the blade. So in inlet, resultant vector is C1, and its horizontal component is CW1, because we are interested the component of the resultant vector which is parallel to the direction of the blade motion. Okay, so this CW1 basically that will be CW1 basically that will be C1 cos alpha 1. Similarly here this C2 is equal to C2, so this is alpha 2. So if it is alpha 2, this is also alpha 2. So this will be C2 cos alpha 2. Coming to the next slide. Now you see the direction, the C1 is in this direction. Seeing the pictorial view of this based on the alpha and beta, whatever it is considered here. So your CW1 direction will be in this direction. Basically this is CW1. Okay. So this is CW2, which is this one, CW2. This is okay, C2 cos alpha 2. And if you see the CW2 is in this direction. So this is your CW2. So now the resultant of these two, because both are parallel vectors but direction is opposite, so the resultant is this one. So we can tell the change of uh, velocity, the change of velocity of the steam jet along the uh, direction of blade motion is del CW2. Okay, because we are interested on this only. This will cause the thrust to rotate. We will calculate the axial thrust also. That is very important to design the bearing. But to calculate the uh, uh, turbine motion, our interest is to find out the acceleration or the change of velocity along the direction of motion of the blade, turbine blades. So which we calculated, that is del CW2, which is del CW, which is nothing but CW1 minus CW2. So this CW1 basically C1 cos alpha 1 and CW2 is equal to C2 uh, cos alpha 2, and C1 is basically coming from the uh, inlet uh, uh, triangle vector summation. That is, there are two vectors, the turbine blade velocity and the uh, inlet steam jet velocity. If you uh, after vector sum, the resultant is C1, and from the outlet triangle, the steam jet exit velocity V2 and the blade motion U, if you take the vector summation, that is C2, and the cost component of C1 and C2 is CW1 and CW2. We want to find out the change of this velocity or the resultant vectors, because from there only we will find out the force which is acting on the turbine blade. Now from the Newton's second law, your force is basically mass into acceleration. So basically the acceleration is change of velocity in unit time. We can write these things m by t, which is basically the mass flow rate. So now the force is, and this del v in case of our uh, analytics, that is CW1 minus CW2. So your F is equal to mass flow into the change of steam jet resultant velocity along the direction of motion of the turbine blade. So which is mass flow into del CW. Now the work done is equal to force into distance, and the power is work done by unit time. So which is for force into distance by time. This distance by time is velocity. So already we found the F is mass flow rate into del CW. So it is come like this, and this is in watt. This P is in watt. This is in watt. Kilowatt means you have to divide by 1000. So this is the power required. Means this is the power of the turbine at the output shaft. This is the uh, vector diagram, or it is called the um, velocity triangle of turbine. So our discussion is today is up to this. This is a very simple concept, but to understand the entire analytics of uh, turbine and its dynamics, you should understand this velocity triangle perfectly. So that's why the first lecture I dedicatedly made on this, and I have uh, elaborated very slowly and from the basics, so that all the people from different streams are also can understand this concept. To understand this concept, you need not to become a specialist in any particular discipline, mechanical, electrical, or whatever may be. So this concept I started from the 12th standard. So hope you have understood and you have learned something. Thank you so much. Thanks for your patience.